What if the general properties of matter at zero temperature could be deduced from the general properties of matter at non-zero temperature? For the daily life, nothing would change, but from a fundamental point of view, this would mean that the third law of thermodynamics could be deduced from the second law of thermodynamics, from the law of entropy increase. It would mean that the third law of thermodynamics would be a theorem, an ultimate consequence from the second law. My name is José María Martín-Olalla. I am professor of physics at the University of Seville in Spain. I am presenting here a video showing the results of a work published in the journal Physica Scripta from the Institute of Physics Publishing Services. Si conoces español, hay una versión disponible de este vídeo en español. Lo encontrarás en el link en la descripción de abajo. Please follow the description below to find useful links from the ahead presentation. I will present this video in section in three parts. First, I will present the problem statement. Then I will revise the stability condition at non-zero temperature. Finally, I will set the stability condition at the absolute zero, and I will present a brief conclusion of this work. First, allow me to show the problem statement. First law and the second law of thermodynamics summarizes the foundation of this branch of physics. The first law introduces the conservation of energy, introduces the energy. Energy is a function, is a property that is common to almost every branch of physics. And the second law is much more specific of thermodynamics and or of macroscopic physics. The second law, the law of the increase of entropy, introduces the concepts of temperature, which is a positive number, and the concept of entropy. The second law also allows us to get the knowledge of the concept of a specific heat or heat capacity. It is the temperature times the derivative of the entropy over the temperature at constant volume. And the second law, the increase of the entropy of the universe, mandates that this quantity must be a positive number. Positive number means that to increase the temperature of the system, we need to supply energy to the system. And in order to decrease the temperature of the system, we need to withdraw energy from the system. First law and second law are independent to each other, but both combined lead to the concept of fundamental relation, which is a relationship between energy and entropy that contains every chunk of information about the nature of the system. Among them, we can get to the equilibrium condition and to the stability condition. The stability condition will play a relevant role in the following discussion. And the stability means or refers to the property of the equilibrium states of a system to remain in time. If a perturbation or an inhomogeneity or a fluctuation within the system arises, then it would trigger processes that would tend to decrease, to mitigate this fluctuation or this inhomogeneity or this perturbation. This means that the equilibrium state would remain in time until an external action forces it out. A stability condition can be expressed as a restriction for the curvature of the fundamental relation. The curvature of the fundamental relation, the second derivative of the energy relative to the entropy 2 times, must be a positive number. I mean, the fundamental relation must be a strictly convex function of the entropy. This can be also expressed as a derivative of temperature over entropy, or simply as T over Cv. So the positiveness of the heat capacity can be viewed in simple terms as we need to supply energy to increase the temperature of a system at constant volume, or we need to withdraw energy to decrease the temperature of a system at constant volume, but they can also be read as a condition for the stability of the system. This is regular stability, and it just means that the fundamental relation cannot be concave, but in a limit case, the curvature of the fundamental relation can be flat. This is the critical stability. This is the critical point, the condition upon which the second derivative of the energy over the entropy 2 times equals 0, becomes equal to 0, meaning that the fundamental relation is flattened out. This gives rise to very large inhomogeneities, very large fluctuations that can be seen in this video, where the critical fluctuations for a liquid vapor phase transition are shown. This is the whole set of relevant evidences for the following discussion at non-zero temperature. I mean, this is always for non-zero temperature, for room temperature, or for a standard temperature condition. There are also two general properties of the thermodynamic systems that refer to the absolute zero. At absolute zero, we observe two independent laws. First, the vanishing of the isothermal entropy, or Nernst heat theorem. I produced a video and published a work on the proof of this theorem that you will have a link in the description below. I will not refer to this problem in this video. The second property is the vanishing of the specific heats at T equals 0, or as long as the temperature decreases. This is known as the third law of thermodynamics, and it is known as the third law of thermodynamics because at the beginning of the 20th century there were no theoretical link between the properties of system at absolute zero and the properties of system above zero temperature. The work published at Physica Scripta just closes this gap and brings out a relationship between regular stability, critical stability, and the third law of thermodynamics. It's not sheltered, it is almost in plain view, because regular stability, critical stability requires a very specific condition for temperatures greater than 0. And this equation can only be observed at temperatures greater than 0 if the specific heat becomes infinite. While for regular stability, if you are at regular condition temperature above 0, then you need that the specific heat becomes positive, which is this relationship. But of course, at the absolute 0, or in the vicinity of the absolute 0, the problem arises because for this equation to hold, you need that the specific heat must vanishes, and it must vanish faster or as faster as temperature. While this condition at T equals 0 requires that the specific heat vanishes slower than the temperature. Let's see that in detail. Confirming evidence of the vanishing of the specific heats collected by Nernst at the beginning of the 20th century shocked the scientific community. The available theory of specific heats developed by Boltzmann during the 19th century considered that the specific heat should remain constant irrespective of the temperature. We should withdraw or supply energy to the system in order to change its temperature. It was the new emerging quantum theory that helped to solve the problem. Albert Einstein and Peter Debye in 1907 and 1912 developed a model of crystalline solid whose specific heat vanished at absolute 0, and they vanished with a fast rate. Probably this feature helped to decouple the existing framework of thermodynamics, the first and the second law, view it as a classic framework from the problem of the vanishing of the specific heat, which was, quotes, quantum in nature, and therefore subject to a new independent law, the third law of thermodynamics. However, from a thermodynamic point of view, the microscopic nature of the system, whether it is classical or quantum, is irrelevant for the discussion of its properties. In other words, we lack a thermodynamic explanation of why the specific heat vanishes at absolute zero. The article published in Physica Scripta helps to solve this gap. Now allow me to explain how stability and specific heat interact. Allow me to show the relationship between specific heat, curvature, and stability at regular conditions. First, we have here a chart of energy versus entropy, and this is the fundamental relation. The fundamental relation is an increasing function of the entropy because the slope of the tangent line is the temperature, and the temperature is a positive number. So this is an increasing function. It is also displayed as with a curvature. So we have here a curvature. The fundamental relation bends in a strictly convex way. That means that the temperature increases as the entropy increases. This is, by the way, a plot for a constant volume condition. The curvature of the oscillating circle is related to the second derivative of the energy over the entropy 2 times, and it is in turn related to T over Cv. This is related to stability because if this inhomogeneity arises and we have this equilibrium state split into 2 portions, one with a larger entropy and one with a smaller entropy, but just taking into account that the average entropy remains at the initial value S, then we would have this kind of condition in which the one portion is heated and the other portion is cooled. I mean, this portion has greater entropy, greater energy, and greater temperature because the relationship is strictly convex, and this portion has smaller entropy, smaller energy, and a smaller temperature. Now, if we draw the second line from this point to this point, we would have at the value of S the average energy of the perturbed state or the perturbed condition. And because this relationship is strictly convex, this average energy is above the original energy. This is this condition here described. And because energy is above the original energy, the system would rather prefer to decay to the original equilibrium state. And then this equilibrium state, I mean, this would go that way until we reach back the initial condition, and this initial condition would be stable. What we are seeing here is how the hot portion is cooled at the expenses of the heat of the cooled portion that is heated. So this is a standard stability and requires that T over Cv becomes positive for this strictly convex condition. If we are at a regular temperature condition, I mean, if T is greater than 0, then Cv must be greater than 0. This is a trivial derivation from this condition. The limiting condition, the critical point, arises when this strictly convex relation becomes flat and the potential is, the fundamental relation is only convex. It is not strictly convex at the point you see the critical energy and the critical entropy. It is only convex, not strictly convex. This means that the curvature here is 0. The radius of the oscillating circle is just infinity. So when we get a perturbation, or our inhomogeneity, we have a condition in which this state and this state, which they have a greater entropy or smaller entropy respectively, they have both almost the same temperature. And the average energy of the new set is almost exactly the same as the energy of the initial state. Therefore, we have here a very soft condition. This is a soft mode, and this state can move here very, very easily, meaning that the inhomogeneity can grow immensely on this condition, which is set but by the idea that T over Cv must be equal to 0. If we are on a regular temperature, this means that the specific heat must become indefinitely large, must come to infinity. But these are only the conditions for regular temperature. For temperatures above T equals 0, we now will be expecting what happens in the vicinity of the absolute 0. Before that, allow me to kindly suggest you to watch the video on the critical opalescence. You can get to know what happens on this very specific condition. The system would exhibit very unique properties. Critical point is not a feature of the liquid-vapor phase transition. It is also present in superfluidity, in superconductivity, in ferroelectricity, ferromagnetism, and ferroelasticity. It is a phenomenon that is associated with lowering the temperature. Therefore, it is a phenomenon that is reminding us that very strange things happen at very low temperature compared to what happens at high temperature. Now, referring to the properties at absolute 0, remember that the fundamental relation that the slope, the tangent line, or the slope of the tangent line to the fundamental relation is the temperature. So arriving at absolute 0 means that the fundamental relation must become flat. The tangent line must become horizontal at the absolute 0. So it is kind of landing an aircraft so that it becomes horizontal at the point of contact with the ground, when the aircraft is landing. And the thing with this tangent line, with this horizontal tangent line, is that we don't crash the aircraft, but just safely land on the ground. Now, the point of view from thermodynamics is a little bit awkward. I mean, it's a little bit unintuitive, because we don't want a very long runaway so that the plane can move freely through the runaway. We need a very specific runaway. We need a very specific curvature so that the system can land safely and stably on the absolute 0. Let's see that. Now let's analyze what happens close to absolute 0, how we can arrive to this condition, how can we land into T equals 0. I have produced here this plot of, again, energy versus entropy, and we have here a state at T equals 0. Just T equals 0 requires here a flat slope, a flat tangent line. So the fundamental relation here must be flat, must go with a horizontal tangent line. Here we have an arbitrary state which is hot, which is a temperature at a temperature above T0 and has energy and entropy which can be set to unity without loss of generality. We can also set this state to 0, 0 without any loss of generality. Well, I mean, I am referring now to landing at T equals 0 strictly. I mean, non-asymptotically. I will discuss the asymptotic case in the near future. So here we have this condition, which is T equals 0, and we have this vertical line, which is a vertical line representing infinite temperature if the fundamental relation here were the tangent line of the fundamental relation here were this straight line. course, this is just a limiting condition, but we have here something which has non-zero temperature, and as much this non-zero temperature can be infinity, which is this line. Now we have here the second line from 0, 0 to 1, 1. Because the fundamental relation is a convex function of the entropy, the fundamental relation must lie below the second line. So just like here, where the second line lies above the fundamental relation, here the second line must lie above the fundamental relation, meaning that we can only leave this point through this narrow set of angles of paths, and we can only get at the absolute zero around this narrow set of paths. Okay, so we need a flat function on this range, and the trivial try for this condition are functions that are simply a power of the entropy. Okay, and if we get a power which is above 2, just 3, 4, 10, and 20, here you can see we will have a path, a landing into the absolute zero that is very flat. The larger the number, the flatter the arrival at t equals 0. So for n equals 3, we have here the fundamental relation s cubed, and we have here the curvature s 6 times s. This means that here we have 0 curvature, and we have here leading or arriving at the absolute zero, landing at absolute zero, unfulfilling the stability condition. I mean, this limit will be 0 at the very 0 point. For n equal 2, we will have the limit condition. We will be landing safely at the absolute zero with 0 slope, and also with curvature, because now if u equals s squared, we have a non-zero curvature at the absolute zero, meaning that this inhomogeneity yields a positive change of energy, which will tend to decrease in time. This is much smaller when you have a cube, s3 or s to the 4th or s to the 10th or s to the 20th. It thus becomes very, very flat, excessively flat. For exponents smaller than 2, we have the same kind of arrival. I mean, this is landing with 0 slope. It's very difficult. It's hard to have a view of that on this plot, because we would need a very smaller scale, but they are arriving flat here, very flat. And we have a curvature that is of this kind for s to the 1 plus 1 over 3 power. We have a curvature that is s to minus 2 over 3. And this means that at the absolute zero, curvature here is infinity, meaning that the radius of curvature here is 0. So we have here an infinite curvature, a 0 radius of curvature, and the point is that on this region, I mean, when the exponent is below 2, is equal to or below 2, we will have here a condition in which the limit of the curvature becomes positive, either a finite number if n equals 2, or infinite if n is smaller than 2. For the specific heat, that means that the specific heat mass vanishes as fast as t or faster. While in the other region, on the other shadowed area range, we would have a condition in which the curvature becomes zero at the 0 point. This means for the specific heat, if this equals 0, that the specific heat vanishes slower than T, or even it does not vanish at all. This case is the case in which the arrival, the landing at the absolute 0 is asymptotic. I mean, this point is truly the entropy can become indefinitely small, indefinitely negative. So this point, the 0, is actually in minus infinity. This behavior, if if the specific heat does not vanish at all, leads to an exponential behavior. And the exponential behavior here cannot be plotted very easily because it requires another scale for the entropy. But we can figure out the shape of an exponential function thinking that we view the exponential function from a very, very large scale. And then we will see something like this. This exponential function would fade away very quickly, and then it would remain flat for a very long period of entropy until the entropy becomes minus infinity. So this boundary more or less describes the behavior of an exponential decay of the entropy, which in turn means that the specific heat is constant and does not vanish at all. So, which are the experimental observations, which are the evidence on this field? Well, we have that most contribution to the specific heat remain into the stable area. The electronic contribution, the Fermi liquid, means that the exponent n equals 1. We have equal to. I beg your pardon. This is n equal to. This is the Fermi liquid, and the specific heat comes to 0 as the temperature. The specific heat is proportional to the temperature. The crystalline solid model developed by Einstein and Debye at the beginning of the 20th century shows the case that the specific heat comes to 0 at a very fast rate of T to the third power to the cube. This means that the exponent for the energy-entropy relation is 1 plus 1 over 3. So it remains stable. On the two-stage contribution to the energy, which is present in some specific system with free spins, this was developed by Schottky at the beginning of the 20th century. This specific heat comes to 0 very fast, which a very steep exponential decay. And this means that the curvature becomes infinity and that you have an stable condition as well. Now, in this region, in the critical region, we have the quantum critical point. There are certain specific systems, mostly cuprates, systems that exhibit normal superconductor phase transition and a very complex and a very intense correlation among the spins of the system that may exhibit a slowly vanishing specific heat. And we are referring to that as a quantum critical point. And the thing of the quantum critical point that this quantum critical point occurs at the 0 temperature. So we are here setting the condition for a loss of curvature and setting the condition for a critical behavior. So let me conclude now. Just as a summary of evidence close to absolute 0. First, specific heats vanish fast regularly close to absolute 0. This can be viewed as that nature abhors alternative behaviors, anticipating that they would not sustain stability condition precisely at absolute 0. Real systems do not usually exhibit critical fluctuation at absolute zero. They show a regular, stable behavior. Notwithstanding this, in strongly correlated systems, critical fluctuations can be observed precisely at T equals 0, as it may happen at any other non-zero temperature. The signature of these critical fluctuations at T equals 0 continues to be the loss of the stability condition, the loss of curvature, as it always happens with critical fluctuation at any other temperature. A new law is not needed to codify the above behaviors. We would need a new law to establish that the specific heat vanishes slowly, close to absolute zero, so that there is always a critical point at absolute zero. Or we would need a new law to establish that critical behavior at absolute zero is forbidden. But we have both behaviors, both the fast vanishing of the specific heat, meaning stable, and the slow vanishing of the specific heat, meaning critical. We never observe a flat, non-vanishing specific heat close to absolute zero. The idea here presented was first publicly aired in a video that shot at Cuentos Cuánticos, a YouTube channel hosted by Enrique Fernández Borja on 30 June 2025. Watch the following link and the commentaries therein. I thank Professor Javier Sebastián Blázquez from University of Seville for his commentaries and fruitful discussions during the revision of this manuscript. Thank you very much for watching this video. Please have a like on this video. The slides are publicly available at the Zenodo server, and my opinions does not link or oblige the institution University of Seville. Thank you very much.